Great. Okay, so today we're going to talk about global energy balances and climate change. So we're going to be thinking big scale here. Our learning objectives are first to describe the global energy balance and the greenhouse effect. So we're talking about water balance on Tuesday, talking about energy balance today. Of course, water is intimately tied into that energy balance because a lot of energy moves with water. The specific heat of water is pretty high. Water can carry a lot of energy into it, and that's very important. That's how hurricanes work, right? That's how weather works. We're going to contrast weather and climate, two different definitions. We're going to connect global climate oscillations to weather and climate patterns over continental US and Colorado, just to kind of understand the context, the climatic context that we're in Colorado. And they'll understand the causes and effects of global climate change on water resources in Colorado. And that was related to the article that I had you guys read. Okay, so kind of a physical relation that is behind all of this is called black body radiation. Stephen-Boltzmann law. No, that's not going to be on the test. But the idea is that a black body, any sort of matter, radiates energy. Okay? And that energy is related to its temperature. And so the kind of different kinds of electromagnetic waves that come off of any sort of, this is kind of a theoretical thing, right? It's not a black hole. Just any type of black mass is going to be related to its temperature. So the sun, surface of the sun is about 57 or 5800 Kelvin. It's got a certain color associated with it. It's also radiating electromagnetic radiation all the way up to gamma rays in this case because it's so hot. But if we're down to different, so we know that things get hot and start showing color when they get hot, right? White hot, even blue hot, depending on how hot things are. But when we're talking about things that are heated by our sun, they heat up and they radiate energy back, okay? And that energy is going to be typically infrared energy. So heat energy, infrared energy, we feel it from the sun. When we feel the sun's rays on our skin, we're feeling the radiation coming in from the sun, the incoming solar radiation. All right, so a lot of that is bounced off the atmosphere and reflected by the clouds and back into space. And then some of it makes it down to our earth and on our skin is what we're feeling. So this is the global energy balance. And the units on this are watts per meter squared. So if you think about, I think a term I heard recently is global warming is related to about extra 4 watts per meter squared on average across the planet, which is about a flashlight held up here. Not a lot of energy, but when you add it up, it's a lot. So what's happening? So just in general, the way the world works, you've got energy coming in, right? So 341 watts per meter squared coming into our planet on average from the sun. And so we get some reflection from the clouds in the atmosphere. Some of it's absorbed by the atmosphere, right? We've got water molecules, we've got greenhouse gases, they absorb that energy. Carbon dioxide, methane, and those molecules in the atmosphere absorb that energy, okay? And then some of it makes through and gets absorbed by the surface, and some of it's reflected back by the surface. And we'll be talking about, when we talk about snow, we'll be talking about this term albedo, which is the reflectivity of snow or really any surface. Obviously, snow being white reflects a lot. When snow melts, the Earth is able to absorb more energy from the sun. You get a positive feedback loop. Okay, so once the energy is into our system, we also have some, okay, so it absorbs energy, right? And then you've got this kind of flux, this kind of ping pong effect where we're emitting energy from surface radiation and it's bouncing back. And this is the greenhouse gas effect, right? So radiation that's emitted from the surface of the Earth just through black body radiation is absorbed by the atmosphere and it's either reflected back or it's absorbed and then emitted back. And that's why we're able to live on our planet. If we didn't have these greenhouse gases, this atmosphere that we live under, all of this heat would bounce right back out, and we would be like the surface of Mars or something like that. It's just brutal temperature fluctuations. Really hot when you're in the sun, and super cold when you're out of the sun. So having an atmosphere is helpful for that reason. Now, we've got kind of within this, you've got just straight up radiation emission from the Earth, this black body radiation. You also have radiation flux from evapotranspiration. So when things evaporate, they take that heat with them. That's why our skin feels cool when our sweat evaporates. The water vapor that's coming off of you is taking heat with it. And so there's a heat associated with that, or a heat transfer associated with that. What else to say? Oh, and then apparently there's a net absorption too. So the Earth is like slowly, the planet itself is slowly heating up by this 0.1 watt per meter squared. And that's kind of going deep down, below the soil. Okay, so this shows the absorption spectrum of different wavelengths of light. And what we see here is just energy. We can just think of it as, light's hitting our planet, it's noon, we're sitting out there in the field on campus and getting a suntan. So what's coming in, this is the wavelengths that are coming in, mostly visible light, a little bit of ultraviolet light, a little bit of infrared light, okay? So the spectrum is the wavelength down here. And, higher energy over here with smaller wavelengths and lower energy over here with shorter wavelengths. So most of it's coming in as visual, a little bit of infrared, a little bit of ultraviolet. And then what's reflected back is solely infrared. So, the Earth isn't emitting UV rays, right? The sun is, but not the Earth. There's also not emitting visible light because it's not that hot. So the radiation that's coming back out into space and hitting the atmosphere is in the infrared spectrum. Okay, and then we look at what's the absorption spectrum for gases in the atmosphere. So one is 100% absorptivity. It means it absorbs all of that radiation. And then, so here's all these gases. So we've got ozone, oxygen, water vapor, carbon dioxide. And so you can see that you've got pretty high absorptions for carbon dioxide, water vapor, a little bit of ozone for these different spectrum that are coming out of our atmosphere. It's nice that ozone absorbs this ultraviolet light, right? We don't like to have those ozone holes, so we don't get all this ultraviolet light coming in. But these are kind of primary constituents of our atmosphere that absorb and retransmit this energy. So our planet isn't evenly heated, right? We know that because if you go to the North Pole, on a typical day it's cold, maybe in the summertime it's not these days. But you get less energy if you think about if this is the sunshine at the equator, the light is most concentrated. Because you're perpendicular with the planet, or the rays are more perpendicular with the sun. And then the farther latitude you get away from the equator, either north or south, that light is spread out more. So that's why it's colder in these regions, because you're just basically diluting the energy. It's spread out over a larger area. But that doesn't necessarily stay the same. We know it's colder in high latitudes and low latitudes, but you get a redistribution of energy from these, what are called Hadley cells. And so at the equator, we have rainforests, right? Because it's so hot down there, you mostly get this upward movement of hot air that when it goes up, and we'll talk about this when we get into precipitation, but hot, wet air rises, it gets cold, and it rains out. So a ton of rain gets dumped at the equator because of that. And then you get these kind of mid-latitude where that hot air descends back down. And then you get another updraft of air. And so it's kind of like these cells of circulation that redistribute this heat energy to the higher and lower latitudes across the planet. These affect trade winds, so the dominant winds in the area, and also affects how, like the jet stream and all those things work. So let's talk about climate. Climate is kind of the big picture, long-term average. Climate is the average annual temperature, Grand Junction, or New York City, or Daytona Beach, Florida. It is these, what's the expected average high temperature in June in a particular area. So it's kind of what we experience because of these big picture global things that happen. It's drier on the western slope than it is, or sorry, so you get more snow on the western slope than you do on the eastern slope. That's a climatic thing. We'll talk about why that is. Here's annual precipitation. Again, driven by these kind of big picture climate factors. Okay, so climate versus weather. Here is our meteorology friend. And I think this was a video I got this out of, but maybe I just took some slides. So weather is what's going to happen on a particular day, right? So weather is going outside saying it's 90 degrees. I'm glad I brought a lot of water today. Climate is, well, I'm going to look at the calendar, and I think on average the high in August 20th is 90 degrees, so I better take a lot of water. Weather is just a particular manifestation on a particular day or hour of climate. So this variability is our weather. If you kind of take the trend line through here, that's your climate. There we go. So weather, climate. And highs and lows, right? What's the high temperature for this month? What's the low temperature for this month? So let's look at Grand Junction, Colorado. Here's our average monthly precipitation, these blue bars. And then we have the high and low temperature in Fahrenheit on average. So on average in August, the high temperature is sitting right there at 90. And we've been beating that for a little while. And Vail, a little bit different, right? What do you see about the pattern of precipitation in Grand Junction versus Vail, Val?
It decreases in June and July, like way more.
So pretty dry during this time of year. Maybe it picks back up. Do you know what happens here typically in the fall? Why there's more rain? We'll talk about it later, but it's called monsoons. And you probably heard of that word monsoon. So it's these kind of late summer thunderstorms that we can get. I haven't been having any of those lately. In Vail, it's a little more distributed evenly in terms of precipitation. Obviously, this would be snow in Vail, but they get a lot of rain too. Not as variable there. All right, so let's talk about climatic oscillations. These are, you've probably heard of El Nino. There's a bunch of these situations where we have these kind of big continental scale changes in sea surface temperature. That's what this is, a map of sea surface temperature, that interact with the weather patterns, that interact with the jet stream to bring more or less moisture to a particular part of the continent, to bring hotter or colder temperatures. And these things kind of develop. No one exactly really knows, the specific drivers of why the ocean gets colder for certain periods of time in this region and hotter for certain periods of time in this region. Right? You've got these big global ocean currents that distribute heat across. We talked about the atmospheric Hadley cells, where the ocean has its own system of currents that redistribute heat. But these what they're called as sea surface temperature anomalies. And anomaly just means departure from normal. So 0 is average sea surface temperature. The equatorial, oh gosh, we'll get there. I'll look at that. I think I spell it out later. It's El Nino Southern Oscillation. Okay, El Nino Southern Oscillation. Shows that the sea surface temperature oscillates, right? It's not a steady thing. It's kind of going cold and then hot, cold, hot, but it's not kind of like staying flat. And so it oscillates up and down between either colder than average and warmer than average. And that has big implications for weather systems in South America and North America. So El Nino, anybody recognize this guy? It's from my childhood.
Chris Farley.
All right. Chris Farley, look him up. He's in Saturday Night Live. He is El Nino. It's Spanish for the Nino. And so what happens with El Ninos in a normal year, kind of basically you can have a year where it's not really strong. There's not like a really hot or really cold situation. You've got, this is the ocean current right here. So the ocean current is coming up the coast of South America and going back out along the equator. So you've got a big upwelling of cold water here when the deep currents hit the continent. That's why there's such an amazing fishery here along the coast of Chile and Argentina, because all this cold, nutrient-rich water is upwelling here, and all the plankton and fish love it. And then it gets to the surface, it gets really hot, and so you kind of have warm water from the surface cooling over here in Australia and Papua New Guinea, New Zealand. But during an El Nino year, things change, and so you got different wind situation, and warm water stacks up over here as opposed to over here. And when you have warmer water kind of closer in this area, well, you get warmer winters in this particular area, and then a lot of influences on precipitation and stuff like that. So you've got folks that are looking at, from like satellite data and buoys out there measuring temperature in the water, that are closely monitoring this region and the surface temperatures, because they want to know, okay, is it going to be an El Nino year? The opposite, La Nina, that's when it's colder. And so here's just a time series of that index. This index is just a composite of temperature departures. And so let's see, I don't know how recent this gets to, but we got out of a La Nina recently. Let's see.
Last year, El Nino.
You know, I don't remember exactly. I don't have the latest on that. Right now, we're in weak conditions, so we don't have strong El Nino or La Nina conditions. This is just a map of when you have El Nino, right here, El Nino. Is it hotter or colder? So blue is colder, warm is hotter. So during El Nino years, much of, let's see here. Yeah. So this is just total average annual, not like what winter versus summer. But on average, it's cooler in the south and hotter in the northwest. And then we have precipitation is also influenced like it. So you can see during El Nino, it's wetter over here, wetter on the coast during El Nino, and then drier on the interior. But this is kind of like a global scale. Let's look a little more kind of zoomed in. So this is Colorado, and we're looking at precipitation during seasons. So blue is wetter during La Nina, and then orange is wetter during El Nino. So La Nina we like because we get wetter conditions during La Nina in the wintertime. That's when all of our water comes. You get some more intense storm events during El Nino in the summertime and in the fall. So monsoons can be stronger during El Nino. But we like La Nina for snow. That's contradictory.
Which was the floods in 2013? Was that any particular?
That was, sorry, guys, let me just go back. We'll talk about that one specifically. Upper Basin versus MSA State. I gotta figure this out because this graph clearly states that it's wetter during La Nina. And then this graph clearly states that it's drier during La Nina. So this is the upper basin precipitation. And you can see here's like the average. During neutral, we're kind of straddle it. During La Nina years, it's drier, and during El Nino years, it's wetter. I need to double check that. I'll get back to you guys. Yeah, the 2013 floods, that was, I think I've got a video of that, and we'll talk about later when we talk about floods and rain. But that was this crazy system of pressure fronts that created this cyclical wind currents, and there's this pressure front that was sitting up against the mountains on the Front Range, and it brought all this moisture up from the Gulf of Mexico. I think it was the Gulf of Mexico anyway, and just for whatever reason, it stalled out there. Just like we have a high pressure front that's stalled out over us right now, that's keeping it from raining. And so that just basically had a fire hose of air moisture and pushing it against the mountains. I don't know if that was related to this, what I'm talking about right here, but it could have been. There's another kind of thing that happens, kind of intercontinental scale, it's called atmospheric rivers. Now what we're looking at is precipitable moisture in the atmosphere from satellite data. So the red is about 5 centimeters of water vapor that could come out. And so these things set up, and people are studying these because they cause massive flood events in California. But they set up in the atmosphere, and they're basically just like a really high concentration river of water vapor in the atmosphere that can then, because of the jet stream, crash into California where there's mountains. And then during an atmospheric river, you can see these are USGS gauges. So black is like the highest on record. Blue is 90th percentile in terms of stream flow. So when this atmospheric river hit north central California, all the rivers were flooding because of this crazy situation. So again, it's one of those things, it's kind of like a hurricane. They form and people study them and try to watch them and understand what happens, but sometimes they're hard to predict. Unfortunately, I don't think atmospheric rivers make it out to Colorado. Okay, so let's talk about climate change and kind of the theoretical underpinnings and evidence behind it. This is a little video, I'm pretty sure. Yeah. So let's take a look at this.
Alex here. Is climate change really human-made? There's been a lot of research and reports published over the years, and I don't blame you if you don't want to read it all. So here's what we know for sure in 3 minutes. Let's get drawing. It all started in 1998 when an ice drilling project was undertaken in the Russian Vostok station in Antarctica. The project yielded the deepest ice core ever recovered, giving access to ice that was 420,000 years old at a depth of 3,623 meters. It supplied data about atmospheric composition and climate through 4 climate cycles. So here is how it all works. The formation of the glaciers results from the transformation of water into ice. During this process, which can last thousands of years, sediments, air, and rocks are stuck into the ice, making millions of layers, one above the other, in chronological order. Over the time, the glacier becomes a million-page history book with the last chapter on the top. The deeper you drill, the older the compounds are. The ice core gave access to climate data, including local temperature, precipitation rate, wind strength, etc. But also, and this is what we are interested in here, the ice core provided direct records of past changes in atmospheric trace gas composition, thanks to their entrapped air inclusions. Then, it was possible to determine the levels of carbon dioxide, CO2, and methane, CH4, at a given time. So, here is what global temperature and atmospheric concentrations of carbon dioxide and methane look like over 4 climate cycles, 420,000 years. So you can clearly see the 4 climate cycles, and you also see that they have very similar spikes and patterns. There is clearly a relationship between temperature, carbon dioxide, and methane. The upper and lower boundaries of the three variables are tightly constrained, which is typical of a self-regulating system. Our body is also a self-regulating system and does something similar in a way. When you exercise, your body sweats as a way to regulate its temperature. Well, on Earth, when concentrations of carbon dioxide and methane go up, global temperature goes up too. Now, here's what happened with the concentration of atmospheric CO2 since 1960. It increased by about 70 parts per million. That is more than 1 part per million each year, indicating significant human perturbation in the self-regulating system of Earth since the beginning of the Industrial Revolution. As this concentration is now way over the upper boundary noted during the last 420,000 years, and as the Earth seems to be a self-regulating system, well, we can expect the global temperature to increase as well, and we are already seeing this worldwide. Since the Vostok research was published, more recent ice cores were performed by the European Project for Ice Coring in Antarctica, the EPICA. They provided data for the last 800,000 years and confirmed the findings in Vostok. So, as the Intergovernmental Panel on Climate Change simply puts it in their 2013 report, human influence on the climate system is clear, and we can safely say that we, human beings, are responsible for climate change. So please subscribe to learn more about sustainability through short animation videos, and thank you for watching.
Okay. Any thoughts or questions about those data? So, you know, there's a lot, there's a big can of worms, right? And it's something that's been politicized over time. We talk about climate change insofar as it affects the water that we have available in Colorado to use. And it's something that I would say the vast majority of people in the water community in Colorado accept. Of course, people can push back or do push back on the cause of it. And I'm not here to argue the cause of it, but based on the evidence, it's clear that we're well outside of the natural fluctuations that temperature and carbon dioxide and gases have over the past 400,000 years. Now, let's look at, let's see, did I copy this? No. Okay, so these graphs right here, these kind of spikes that go up and down. Does anyone know what causes those climate cycles, those 100,000 year approximate climate cycles? It's kind of, that's probably going to be related to some of the spikes that you see in between them. But those big 100,000 year cycles are actually related to the tilt of the planet. So the planet sometimes, so it has these eccentricities in its orbit, and sometimes it's a little bit closer to the sun, and sometimes it's a little bit farther away from the sun. And that happens over a cycle of about 100,000 years. I can't remember exactly if it's, you know, if it's this tilt or if it's this something like that. So there's this crazy thing, and it's related very closely with the ice ages and stuff like that. So that was the kind of big picture fluctuations that you saw there. Okay. All right, so let's just look at what's been going on in the past century or so, 150 years. You've got, so average global temperatures, and this is called anomalies, so this is departure from average. So, and I think there's some average maybe that happened right here that they're pegging it at, because these are all lower. So it's colder, and then kind of normal, quote unquote normal. Previously in the 1800s, there's actually the little ice age that happened there. I can't remember the cause of the little ice age, but it was, yeah, when your grandparents or great-grandparents talked about walking through 6 feet of snow to get to school, that was real. It was colder back in the day. Since then, there's been a clear increasing trend. Sea level is increasing because of that. Sea level is increasing because we're melting glaciers, And also, as water heats up, its volume increases just by becoming less dense. So you've got this kind of physical expansion of water as well. And then here's our greenhouse gas concentrations. We've got carbon dioxide, methane, nitrogen oxide. And then just looking at fossil fuels, carbon dioxide emissions. So this is the time trend of fossil fuel emissions, as well as cement. That's a really big component of greenhouse gas emissions. And then forestry, so cutting down trees, burning forests, that sort of thing. So here's cumulative emissions in gigatons on average between this time frame, and then here is what it looks like if we go all the way to 2011. So it's just kind of from a physics standpoint, more carbon dioxide, methane in the atmosphere. We go back to that energy balance. We're absorbing and reflecting more of the emitted of the energy that makes it through to the Earth's surface. It's getting trapped in the atmosphere, reflecting back down to our planet, heating us up. So here's a look at temperature change over the last 50 years. So that 2014 to 2018 average versus this baseline. And so what's happened? Well, it's not 100% warming everywhere, right? So there's been some cooling signatures in some parts of the area. The North Pole is heated up incredibly. This is where we have permafrost that hasn't melted in maybe forever, or since it formed, that's melting up here. Greenland's massive tunnels of water are emptying out of Greenland as the ice sheets and are sloughing off. And then we got this hot spot here happening out in the southwest, which we'll talk about. So this is from that article that we read and from the Washington Post, and they did an analysis of temperature data collected by NOAA, National Oceanic and Atmospheric Administration, and they noted some, basically what's changed from 1895 to 2019. Well, believe it or not, Alabama, Mississippi, this kind of Mississippi Delta area got a little cooler. You ask the people down there, they wouldn't tell you that's cool, right? That's kind of a hot and sweaty part of the country. But other areas have gotten hotter than normal. And Los Angeles has been getting hit hard. This whole area is on fire right now. Southern Oregon, as well as this kind of area between on the western slope of Colorado and eastern Utah is heating up dramatically. Here's just a look at the data, the kind of time series data. So these are temperature differences from average. So on average in the US, if you lump everything together, it's about a 1 degree Celsius. But if you look at Mesa County or pick any of these other counties, that trend line's much steeper. And what's going on there? Well, it's probably pretty complicated, but one of the easiest explanations to come by is that as we dry out, there's less water in the soil, less water in the atmosphere, and that heats the ground up faster. We'll get into evapotranspiration in a week or two. And the idea is if you have wet soil, you go out there on the grass outside and you sit on that soil, you can just feel on the grass, you can just feel the humidity coming off of it, right? That's evaporation happening. So that's all that water vapor leaving. If that were just concrete or if that were just dirt or rock, it'd be a lot hotter, right? That's going to heat up and just absorb that heat and let it go, as opposed to leaving the heat through water vapor. So that heating effect can be a positive reinforcement and result in things becoming hotter and drier, which is unfortunate. All right, let's take a breather. I need a water break, and we'll come back in 5 minutes and talk about climate change and extreme weather.
Yeah, I know, that's what I was looking at. Like the angle at which like the sun hits or whatever. Yeah, that would be pretty cool. Yeah. Too bad we never learned that stuff.
Make me want to move to Canada.
Pretty hot up there. How's it?
I just want to read that.
I went there like 2 or 3 years ago. Kind of like just like Denver, but yeah, it's not really like. Well, I was in the city. I was in Toronto. And honestly, kind of just like Denver.
It's like,
Yeah, it's just like to feel like the scenery. The only thing that changes a lot is like the money. Things are kind of expensive. I don't think they take taxes for.
I think the money was
They pay a lot
less.
of taxes. Yeah.
yeah,
I used to want to move to French Canada, but
yeah, I don't like this 100-degree every day stuff that's going on.
yeah, it's way too hot.
I'll give it a balance.
Like a place that don't get too hot, but don't get too cold. They hate the cold, they hate the warm. In between.
French Riviera, that's
It's
it's like 80 all year or something.
usually
It's not 80 all year. It gets colder, but it doesn't get cold. Like it gets warmer now with like, it used to not get too warm, but now like over the years, it gets warmer. Even where I live, when it used to be cold all the time, it gets warm now. And that's not convenient. We don't even have AC.
Yeah,
It used to be a cold
No,
place,
they
but
think
we
too,
used
but
not to
no.
have AC.
that's why a bunch of people die in like Europe, right? There's no BSAC.
Yeah.
I don't like.
See here, it's like, yeah,
Like it's just like.
Don't rub it in.
Just slide up.
Don't rub
it in. I could actually like slides.
okay, guys, let's talk about climate change attribution. So the idea of attribution is what can we attribute this specific weather event, this hurricane, this flood, what can we actually attribute to climate change? And so here's a little cartoon that gets at it. So you cannot point to a particular extreme weather event and blame it on global warming. So Hurricane Harvey happened, it flooded Houston. We can't blame the existence of Hurricane Harvey on global warming, but you can say that on average, because we have a hotter planet, that means we have more water vapor in the atmosphere, more precipitable rain, potential to precipitate rain. It's hotter, we get more extreme things happening, droughts, floods. So on average, we expect to have stronger hurricanes, right? We expect to have more rain in a flood event or a big rainfall event. We expect to have more fires, more drought, that sort of thing. So things are becoming more extreme in terms of weather or climate. So there was a study that, this is a climate attribution study, quantitative attribution of climate effects on Hurricane Harvey's extreme rainfall in Texas. So what they ended up doing is you can model a hurricane. You can create a numerical model that says, okay, here's our hurricane. We feed it, heat. It's got that kind of numerical modeling that requires, three-dimensional numerical modeling that requires to do a hurricane. And you can see what would happen if the water vapor in the atmosphere and the temperature were a little bit different, right? How much flooding would have actually happened. So what this says is that their findings post-1980 climate warming could have contributed to the extreme precipitation that fell in Southeast Texas in August 2017 by approximately 20%, with an interquartile range of 13 to 37%. So somewhere between 10 and 40% of the rainfall that happens is attributable to post-1980 climate warming. And if you want to read more about how they did this, again, it was with modeling. That's the kind of thing that you can attribute to climate change, not the existence of the hurricane itself. So there's a lot of studies. Obviously, we're interested from a water management standpoint about what's happening in Colorado. And there's a clear temperature trend. We've seen this in the Washington Post article and elsewhere. So this is departure from average temperature over this time frame. And so we had cooler periods, cooler and wetter periods, and then, you know, with punctuations of hot, dry periods. And now everything's just kind of hot these days, with some exceptions. So what's going to actually happen? So temperature, we know temperature is going up. We've already observed it. We're experiencing that. What's going to happen with precipitation? Well, that's a lot harder to predict. And you can see that these light colors are pretty much insignificant. These are modeled projections, global climate models. It's really hard to project what's going to happen because precipitation is so variable. The temperature trend is very clear. The physics are very clear. But precipitation is related to the jet stream. It's related to you know, those atmospheric rivers that come in. There's a lot of noise in the precipitation, so it's hard to find a signal in what could actually happen for us. This is really important because it's a tough nut to crack because so much depends on how much rain and snow comes out, especially snow in the Rocky Mountains. And this is the upper Colorado Basin right here, this kind of gray area. This is the lower Colorado River Basin. We've got Colorado, Wyoming, Utah, Arizona. And so here's our Colorado River, here's Grand Junction. And what these green dots are diversion points. Either up here, these are intercontinental or trans-mountain diversions, bringing water over to the Front Range for Denver, Fort Collins, Colorado Springs. And then we've got all this water is coming down and it goes into different reservoirs. We got Lake Powell right here with Glen Canyon Dam, Hoover Dam, at Lake Mead, and then a bunch of different dams along the way as we make our way down to Mexico. If we look at this map, this shows us kind of the relative thickness of water. The relative thickness of the river is kind of how much water comes out of it. And so what do you note when you think about if this is our continental divide right here? Dylan, what do you note about the thickness of the rivers on either side of this continental divide?
They're a lot thicker in the western slope.
Yeah, why is that?
Because there's more surface area in the higher country to gather that water. So, I mean, it's all going to run off the western side of the continental divide. There's just more precipitation sitting on the ground on the western side.
Yeah. Yeah, that's sort of like the idea of the kind of area. That's really interesting. Have you heard, I heard this saying that if you were to take Colorado, put a blanket over Colorado and it drape it over all the mountains and valleys and canyons, and then you were to stretch it all out, it would be as big as Texas because of all that vertical area that we have. That was a quote I heard. I haven't tried that myself, but
Is that true or is that? Okay.
I think it probably is. And we could try it in GIS. We could do that calculation. But so that's the mountains obviously play a big role, and the idea is you know the jet stream goes from the west to the east, and our precipitation is coming from the Pacific Ocean here and then down here. And as it hits these mountains, more snow is going to be falling out on the western side than the eastern side. And it's called the orographic effect. We'll talk about that in a couple of weeks. So the west is blessed with more water, and so we got more population over here. So that's why we have all those transbasin diversions. Here is how water is used in the upper Colorado Basin. This is hydroelectric, 60%, right? This is Glen Canyon Dam, all the dams that we have up here typically have hydroelectric on them. We're not consuming water with that. We're just, it's a use there that's documented. Irrigation is a huge part of what's actually consumed. Some of this is returned to the river, either via groundwater or return flow in canals. Then we look at the interbasin transfers. So this is 6% of the water that's going over to the Front Range or other parts of the basin or outside of the basin. And then we look at actually what are we consuming? Domestic supply, right here, public supply 1%, commercial teeny tiny, thermoelectric consumed 1%. So this little slice right here is what you and I use when we turn on the bathroom, the faucet in the bathroom, the showers, dishwashers. I don't know if irrigation accounts for urban irrigation or not, but it's still a teeny tiny sliver. But this is agricultural irrigation by and large.
It's hydroelectric consumption just because that amount of water has to be in the river.
Yeah.
At the point of, or the end point.
From a water rights perspective, that's why they document it, but it's not going up into the air or anything like that.
So the self-supply domestic, I mean, this would be a super small sliver, but when you think of all the wells in Colorado, is it accounting for something like that, or is this talking just precipitation from the runoff?
So self-supply domestic would be, so domestic meaning residential.
Right, so if you have a residential well, though.
But how much water are you using per residential well?
Exactly, that's why I was wondering if they account for that, because I mean, there's a lot of wells in Colorado.
They do, and that's what this teeny tiny, they don't give us a percentage there, but it's a teeny tiny sliver. I should actually get a table and put those numbers up there. But the residential wells, they don't have a big enough impact really to regulate. Because so if you have, I think you have to have an acre of land, you can put a domestic well in there on that land without going through, you got to get it permitted, but you don't have to go through water rights or anything like that. Everyone with at least an acre of land can have a well for their house. So it's this. So the wells that fuel agriculture, that's what's in here. So you go to San Luis Valley, they're pumping the Lugo aquifer there to water their potatoes. All right, so we've got a lot of uses, right? We've got a lot of water coming out of Colorado, a lot of uses, not just within the state. This is the uses across the whole basin. And back in the day, people realized that, well, we need to come up with some agreement about how to allocate and distribute this water. So in 1922, the Colorado River Compact was signed. And this was between all of the states from Colorado down to California. And the way it worked is they divided the basin up into two parts. So the upper basin, which the Lee's Ferry is the end of that. So that's just downstream of Glen Canyon Dam, kind of the start of the Grand Canyon right here. Has anyone been down there? Grand Canyon, pretty cool spot. If you get a chance, definitely check it out. So there's a very historic gauge called Lee's Ferry gauge. A ferry is just a place where they cross the river. It's like the one accessible point for wagons and whatnot for hundreds of miles on either side. So that marks the upper basin. So everything above that is upper, and then everything below that is lower. And so it says that the upper basins get 77.5 million acre feet a year. The lower basins get the same. That has to be delivered. 7.5 million acre feet has to be delivered downstream, and then they also have another million acre feet from the Salt River and the Little Colorado River. So that's the 8.5. And then Mexico gets a paltry 1.5 million acre feet. And of course, the US has gone back and fought over that even. So it's highly contentious. And then on average, so this 7.5 million acre feet, it has to go over 10 years. So on average, 75 million acre feet need to be delivered downstream of Glen Canyon Dam over 10 years. That was in 1922. And prior to 1922, there's actually been a book written about this. The water supply was actually really high. There was a wetter year, and even beyond this, they had some indication that it was a really wet period of time. So we didn't have a lot of data, but the data that we did have indicated that there was a lot of water. Somehow they came up with the idea that there's 15 million acre feet available in the upper basin.
Is this that study that we did for?
Do you remember that?
Yeah.
Yeah, we did this in statistics. So you got a little taste of this. And yeah, so we looked at how, what the actual thing is. And it turns out, well, it was actually wetter, and on average, maybe we don't have 15 million acre feet. And we still are required, the upper basin is still required to deliver that water to the lower basin, even if it doesn't exist. So that's why we might need to think about readjusting that. Okay, I'm going to skip this part since we're getting close to the end. and maybe we'll talk about it first thing on Tuesday. But what's going on right now? What's the climate look like right now? So here's some maps. Just pulled these off the internet. And what it's showing is the percent of average precipitation over a recent window. And here we see in the west that things are very dry. In our part of Colorado, right here, we're looking at somewhere around 50% of average precipitation that we've gotten this year so far. So that's not looking so good. Temperatures on average looks like it's a little bit hotter in the plains and certainly warm here in Western Slope. So what's the outlook? So this is the 3-month outlook for precipitation probability. And we're looking at some lower precipitation continuing to happen. And this probability of below. Yeah, so the probability of being below average is pretty high in this particular region. And then temperature, it's going to be pretty hot still. So we're looking at some pretty intense drought conditions right now. Okay, so that was a lot to cover. Let's just talk about what's happening right now for this class. For the homework, we've got, so we got a couple things. So let's talk about this. So we got readings. Chapter 2, I've posted this. It's a PDF. And it's just talking about different water data that we collect, different ways, different kinds of data that we collect and why. And so that's in this PDF that's on Canvas. There's a discussion associated with that. So you're going to find a hydrologic data source online and then present what's measured, why it's measured, what frequency it's measured, how far back the record goes, and then how the data are collected and who uses it. So we just want you to look at specifically data and how it might be used and how it's collected. Obviously, stream gauge data is an obvious one. So hopefully not everyone does that because there's a lot of other hydrologic data out there. And I give you some links and some ideas about what to look at in the discussion. So that's a discussion. That means you do some stuff, you post it, and then you respond to one of your peers about what you might have learned from what they did. And then we also have homework number 1 that's posted. So let's take a look. I'm going to